Welcome to the deep dive. We tackle complex stuff and try to give you the essentials fast. Today, we're kind of digging into the chemistry behind something that powers pretty much everything, from your phone to, well, the entire grid,
Yeah.
rechargeable batteries.
Yeah, you really can't overstate how important they are. And it's not just, the small gadgets. Batteries are critical. Think emergency power, UPS systems for hospitals, big storage for solar and wind, and just making sure your car starts. They're the hidden workhorses.
Right. So our mission today is to get a solid handle on the big three secondary cells, the rechargeable ones used in these critical spots. We want to look past the marketing speak, understand how they're built, what the key performance numbers mean, and crucially, the risks involved with each type.
Exactly. We'll look at the evolution. You've got the old reliable lead acid, the powerhouse nickel cadmium, or NiCad, and then the super dense but tricky lithium types. We need to cover the hazards too.
Okay, let's start with the classic, the lead-acid battery. It feels like ancient tech, but it's still everywhere, especially in cars. So fundamentally, what's inside one of those 2.1-volt cells?
Well, the beauty of lead acid is its simplicity, really. It's a secondary cell, meaning you can reverse the reaction, recharge it. You've got two main parts. The positive plate, that's lead dioxide, PbO2, and the negative plate is spongy lead, just Pb,
Okay.
and they sit in the electrolyte. When it's fully charged, that's a mix of about, say, 36% sulfuric acid and 64% water. Pretty straightforward.
So a normal 12-volt car battery just strings six of those 2.1-volt cells together in series. Simple enough. But measuring the charge isn't just about voltage, is it? It's tied to that chemical mix. How do we actually check the state of charge?
Yeah, voltage gives you an idea, but the real measure is the specific gravity of that electrolyte. You use a tool called a hydrometer. Fully charged, it should be dense, reading somewhere between 1.275 and 1.300. And here's the cool part. As it discharges, the acid gets used up forming lead sulfate on the plates. So the electrolyte becomes much more watery and the specific gravity drops.
Ah, okay. And if you let that process run too long, if it gets too watery, that's bad news, right? Permanent damage.
Absolutely. You have to recharge it before the voltage per cell dips below about 1.75 volts. Let it go lower, or worse, let it sit discharged, and that lead sulfate forms hard crystals. That's sulfation. It basically clogs up the plates and permanently cuts down the battery's capacity.
That sounds like a real pain, especially for anyone dealing with cold winters.
Oh yeah, cold is a double whammy for lead acid. First, the cold itself slows down the chemical reaction. Less efficient. That's why your car might struggle to crank over on a freezing morning. The battery just can't deliver the current as effectively. Second, and this is critical, if the battery is discharged, that electrolyte is mostly water. So in really cold weather, it can actually freeze solid.
Freeze, like physically break the plates or the case?
Exactly. Ice expands, it can crack the casing, damage the plates. It's irreparable damage, so keeping it charged in winter is vital.
Okay, let's talk about the different types. The basic flooded cell, cheap, common, but maybe not the safest.
That's the standard car battery most people know.
Yeah.
The big drawbacks are safety and upkeep. During charging, it produces hydrogen and oxygen gas. That mix is explosive, so you need good ventilation wherever you charge them.
Right. Don't want sparks nearby.
Definitely not. Plus, the electrolyte is liquid acid, so it can spill, it's corrosive, and you have to periodically top it up with distilled water as it evaporates or gases off.
Okay, so spills and gassing were problems. The industry came up with the gelled electrolyte cell, the GEL battery, to fix that.
Correct. GEL cells mix the electrolyte with silica to create a thick gel. That immobilizes it. So boom, maintenance-free, non-spillable. And importantly, the gases produced during charging tend to recombine internally. Big safety improvement.
But there's always a trade-off, isn't there?
Always. The downside with GEL was current handling. They're quite sensitive to high amperage, both charging and discharging. Too much current can actually scar or create pockets in the gel near the plates, which leads to premature failure.
So GEL solved spills, but wasn't great for high power demands. What came next?
The next big step was the absorptive glass mat, or AGM cell. This is really the state of the art for lead acid now. Instead of a gel, it uses a porous mat made of glass fiber soaked in the electrolyte. It holds the liquid, but it's not a solid gel.
Oh, so it's still sealed, maintenance-free, gases recombine.
Like,
GEL.
exactly. Same benefits there. But the crucial advantage of that glass mat is its very low internal resistance compared to gel.
Lower resistance means less voltage drop when you pull current.
Precisely. So AGM can handle much higher charge and discharge currents. It maintains a higher voltage under load and delivers more power for longer, especially for high-rate demands.
Now, you mentioned these last two. GEL and AGM are often grouped together.
Yeah, they're both types of valve-regulated lead acid, or VRLA batteries. They have a one-way pressure relief valve. It stays sealed normally, letting gases recombine. But if something goes wrong, like severe overcharging and pressure builds up too much, the valve vents to prevent, the battery case from rupturing.
And this VRLA tech, you said it changed infrastructure? How so?
Think about it. Flooded cells needed dedicated battery rooms, explosion-proof construction, forced ventilation systems. Really expensive and space-consuming. Because VRLA batteries are sealed, non-spilling, and handle their own gases internally, you can put them almost anywhere.
Like right next to the equipment they're backing up.
Exactly. Inside server racks, telecom closets, on the data center floor. No need for that separate, specially built room. VRLA made reliable UPS backup much more practical and affordable for all sorts of buildings. It wasn't just about battery performance, it changed building design.
Okay, so we've covered the lead-acid workhorse, but sometimes you need something tougher or lighter or just different. That brings us to nickel-cadmium, NiCad, used in power tools, sure, but also massive utility backups, right? Up to 40 megawatts.
Yeah, NiCad fills a specific niche. The chemistry is different. Positive plate is nickel hydroxide, negative is cadmium hydroxide, and the electrolyte is potassium hydroxide, which is a base, not an acid.
Yeah.
And the voltage is lower per cell, about 1.2 volts nominal, open circuit.
1.2 volts. So for a 12-volt system, you need 10 of them in series.
That's right, 10 cells.
So if VRLA lead-acid got safer, and we know lithium is way lighter,
Yeah.
why stick with NiCads, especially given the cadmium toxicity? Why are they still the choice for those huge industrial backups?
That is the key question. It boils down to ruggedness and cycle life, especially deep cycling. NiCad's advantages are significant in those areas. They have low internal resistance, so they're great for delivering massive power instantly. High-rate discharge is excellent.
Okay.
It lasts a long time in storage. They work incredibly well over a wide temperature range, and importantly, they don't freeze when discharged like lead-acid can.
Yeah.
But the killer app for utility use. You can discharge them completely flat, then recharge them over and over without significant damage. That deep cycle capability is something that would destroy lead-acid or lithium chemistries quickly.
So for applications needing constant deep cycling, that ruggedness outweighs the toxicity and weight issues.
In many critical industrial scenarios, yes. But the downside is real. Cadmium is nasty stuff.
Yeah.
Carcinogenic, highly toxic, especially to aquatic life. That's led to bans in many places for consumer goods. And disposal is complex and expensive, which eats into their cost-effectiveness sometimes.
Okay, understood. Now let's shift gears to the current star, lithium. The energy density is just massive, right? Tell us about the scale difference.
Oh, it's night and day. A modern lithium-ion battery might store around 150 watt-hours per kilogram of weight.
150 weight kilograms. And lead acid, even the good AGM ones.
Maybe 25 weight kilograms, maybe 30 on a good day.
Hold on, so you're saying, what, 6 times the energy for the same weight?
Roughly, yeah. Or put another way, you get the same energy for about 1/6 the weight.
Right.
That's why everything, portable phones, laptops, electric vehicles, took off. It enabled that miniaturization and range.
It really did change everything. But that much energy packed so tightly, it comes with risks and complexities.
Big time. Financially and safety-wise. Lithium cells often need strong, sometimes pressurized metal casings. And they absolutely require built-in safety features, usually a pressure-sensitive vent in case things get too hot and gases build up.
Yeah.
And also something called a PTC switch, positive temperature coefficient. It's like a self-resetting fuse that shuts off current if the cell overheats.
Let's dive into those risks. What are the main limitations and dangers with lithium?
Well, first, they're surprisingly fragile chemically. Unlike NiCad's tolerance for deep discharge, if you discharge a lithium battery completely, it's basically toast. Destroyed.
Permanently.
Permanently.
Yeah.
And another weird thing, they start degrading the moment they're manufactured. Shelf life is only maybe 2 to 3 years, whether you use them or not.
Seriously. So that spare laptop battery I bought and stuck in a drawer, after 3 years, it's probably useless, even if I never charged it.
Pretty much, yeah. The internal chemistry just breaks down over time. It's a major drawback.
Wow.
Which is why they need sophisticated electronics on board the battery management system, or BMS. It's a little computer constantly watching voltage, current, temperature, state of charge, trying to keep the cells happy and prevent damage.
And if that BMS fails or the battery gets damaged physically,
then you face the biggest risk, thermal runaway. It's a chain reaction. One part of the cell overheats, which causes more heat, which spreads.
An unstoppable feedback loop.
Pretty much. It can get hot enough to ignite the organic solvent used in the electrolyte.
Mhm.
And lithium fires are notoriously difficult to put out. That's the major safety concern.
Okay, so fragile, limited lifespan, needs complex management, fire risk. But there must be a reason beyond density. Do they have other advantages?
They do have one other big plus. They hold their charge incredibly well. Self-discharge is super low, maybe only 5% per month. Yeah. Much better than NiCad or lead acid. So for devices that sit unused for long periods, they're ready to go when you need them.
All right, let's get into some physics that really matters in the real world. We need to talk about internal resistance, often written as resist. You mentioned it briefly, but why is it so critical for actual battery performance?
Right. It's the hidden killer of performance.
Mhm.
Think about it.
Yeah.
The plates, the electrolyte, the connections inside the battery, none of them are perfect conductors. They all have some resistance. So when you draw a current from the battery to power something, you get a voltage drop across that internal resistance. It follows Ohm's law. Voltage drop equals current times resistance. Weiler's I times R wow.
Okay, so the voltage you actually measure at the terminals when something's connected, the closed circuit voltage is always going to be lower than the battery's theoretical voltage, its EMF or open circuit voltage.
Always. The simple formula is terminal voltage equals EMF, current X internal resistance. And the key thing to grasp is this. The more current you try to draw, the bigger that internal voltage drop becomes, and the lower the voltage at the terminals.
That's why car headlights dim when you crank the engine, right? The starter motor draws huge current.
Exactly. Perfect example. The high current causes a big internal voltage drop, leaving less voltage for the lights.
And you said for lead acid, this gets much worse in the cold or when it's discharged.
Drastically worse.
Right.
As a lead-acid battery gets colder, or as it discharges, its internal resistance goes up, sometimes way up. So now when you try to draw that same large current for the starter, the voltage drop is even more severe.
So a battery might seem okay when you test its voltage with no load, but its high internal resistance means it just collapses under the heavy load of starting an engine, especially in the cold.
Precisely. That's why just checking the open circuit voltage isn't enough. You have to test batteries under a realistic load to know their true condition and performance capability, especially for critical applications. Internal resistance tells the real story.
Makes sense. Now, regardless of the chemistry, there are some universal safety rules when working with these things. Let's recap those.
Okay, first, the gassing hazard, mainly with vented types like flooded lead acid. Charging releases hydrogen gas. It's explosive. So, Rule 1, ensure adequate ventilation. Rule 2, eliminate ignition sources, no sparks, no open flames near charging batteries.
That explains the proper way to jumpstart a car, right? Connecting the last negative clamp to the engine block or frame away from the battery itself.
Exactly. Any spark occurs away from potentially concentrated hydrogen gas coming off the battery vents. It's a simple but vital precaution.
Okay, hazard 1. Explosion. What's next?
Hazard 2, chemical burns. The electrolytes are corrosive. Sulfuric acid and lead acid, potassium hydroxide, a strong base, and NiCad. So personal protective equipment, eye protection, face shield, gloves is absolutely mandatory when handling batteries or electrolyte.
Got it. Explosion, corrosion. What else?
Charging procedures. Always, always follow the manufacturer's specs for charging voltage and current rates. This is especially critical for VRLA types, the AGM and GEL.
Why them particularly?
They're much less tolerant of overcharging than old flooded cells. Because they're sealed, excessive gas pressure from overcharging can damage them permanently, or worse, potentially lead to venting or rupture. Flooded cells just bubble more.
Okay. Anything else on safety?
Yeah, one more common mistake. Connecting batteries in parallel improperly. If you connect a fully charged battery directly in parallel with a deeply discharged one,
Oh, bad idea. Huge current flow.
massive circulating current flows from the charged battery into the discharged one, almost like a short circuit. It can overheat both, damage them, and potentially cause the charged battery to vent violently or even explode. That's why boost procedures are specific.
Right. Connect positive to positive, then negative on the good battery to the frame ground on the dead car, never directly to the dead battery's negative terminal.
Correct. Minimizes risk. And related to that, never let a lead-acid battery discharge completely or sit discharge. We talked about sulfation. NiCads, remember, can handle full discharge, but not lead-acid.
And don't forget the freezing risk for discharged lead acid.
Never forget the freezing risk.
Okay, for big applications, UPS systems, solar storage, you're not using just one battery. They'll get wired together into banks. What are the main ways to configure them?
There are a few basic ways, depending on what you need. If you need higher voltage than a single battery provides, you wire them in series. positive of one to negative of the next, and so on.
Voltage adds up, but the capacity, amp hour, stays the same as one battery.
Exactly. The downside is, if one battery in the series string fails open, the whole circuit is broken. The whole bank goes down.
Okay, what if you need more capacity, more runtime, but the voltage is fine?
Then you wire them in parallel. All the positive terminals connect together, all the negatives connect together. Voltage stays the same as a single battery, but the capacities add up.
And if one fails in parallel?
It's generally less catastrophic. The other parallel batteries can usually continue to supply power, although the total capacity is reduced. It offers more redundancy.
What if you need both, higher voltage and higher capacity?
Then you build series parallel strings. You make several identical series strings to get the voltage you need, then connect those strings in parallel to get the total capacity.
Sounds more complex to manage?
It is. You have to be careful to ensure all the strings charge and discharge evenly. Imbalances can lead to problems. That's why monitoring is key.
Is there a simpler, albeit maybe more expensive way for large systems?
Yes, modular systems. These often involve individual battery units, maybe rack-mounted, each with its own built-in management and monitoring. It's the highest cost initially, but it simplifies maintenance, fault finding, and replacement significantly. You just swap out a faulty module.
Okay, configuration's covered. Let's finish by nailing down those ratings you see on battery labels. The most common one people probably recognize is the ampere hour, A rating. What exactly does that tell us?
The A rating is a measure of total energy capacity. It's basically current multiplied by time. So if battery says, for example, 48A at an 8-hour rate.
The rate matters.
Hugely. It means it can deliver 6 amps, that's 48 divided by 8, continuously for 8 hours before its voltage drops below a certain point, usually around 91% of its nominal voltage. If you draw current faster, the total A capacity you get will be lower.
Okay, so it's used for planning how long something can run, like emergency lights needing to stay on for half an hour?
Precisely. You calculate the load current, figure out the required time, and spec a battery with enough A capacity at the relevant discharge rate.
But as we discussed, total capacity doesn't mean much if the battery can't deliver the power quickly when needed. That brings us to cranking amps, CA, and especially cold cranking amps, CCA.
Right. These are all about power delivery, especially for starting engines. CCA is the crucial one. It tells you how many amps the battery can blast out for 30 seconds at a seriously cold temperature, 0 degrees Fahrenheit, which is minus 17.8 Celsius, before the voltage per cell drops below 1.2 volts.
So CCA is the real test of starting power in harsh conditions.
Absolutely. Forget the A rating when choosing a starting battery. You need to look at the CCA. Does it meet or exceed what the engine's starter motor requires?
And starter motors draw a lot of current, don't they?
Oh yeah. Typically anywhere from 450 amps for a small car up to 900 amps or even more for large diesel engines. The battery's CCA rating must be sufficient, factoring in that internal resistance and voltage drop we talked about.
Okay, one more rating. Reserve capacity, RC. What's that measured in?
RC is measured in minutes. It's specific to lead-acid batteries. It tells you how long, in minutes, a fully charged battery can sustain a moderate load of 25 amps before its voltage drops down to 1.75 volts per cell, which is considered fully discharged for this test.
So it's kind of like if your car's alternator fails while driving, the RC rating gives you an idea of how many minutes you have to run essential systems, like ignition, maybe minimal lights, before the battery dies completely.
That's exactly the idea behind it. How much time do you have to safely get off the road? Hashtag outro.
Wow, okay, so summarizing this deep dive. We've seen lithium offers incredible energy density, but it's fragile, has a limited life, and needs careful management to avoid, well, fireworks.
Right. Then NiCad, despite its toxicity, provides that rugged, deep cycle performance vital for some really heavy-duty utility applications.
And lead acid, the old reliable, evolved into VRLA, AGM, and GEL, which dramatically improved safety and practicality for indoor backup power systems.
And throughout all this, safety regulations and proper procedures are paramount, especially when you scale up these systems into large banks. Electrical codes, like the CE code, have very specific rules for battery rooms, ventilation, wiring methods, all designed to manage those risks, like corrosion and explosive gases.
So we often get fixated on that ampere hour rating, thinking bigger capacity is always better. But for the really critical jobs starting a truck in sub-zero weather, keeping life support running during an outage capacity might not be the most important number. Here's the final thought for you. Why should you remember that cold cranking amps, measured down at negative 17.8 degrees CT, and understanding internal resistance are often far more critical indicators of whether a battery will actually perform when you need it most, compared to just looking at the A capacity number?
Because, well, the amp hour rating tells you how long the lights could stay on. But CCA and internal resistance tell you if you can even turn them on in the first place, especially when conditions are tough. For critical tasks, that instant "can it do the job now" is everything. Total energy is secondary if you can't access it